Bom dia a todos. Professor Aníbal, penso que já poderá começar a sua sessão.
Então, muito bom dia a todos. Quero começar por agradecer o convite para estar presente neste segundo dia do seminário. Desejar a todos um bom dia. Espero que seja um dia cheio como o de ontem e vamos começar este seminário neste segundo dia por uma apresentação do professor João Ramôa Correia, que é professor no Instituto Superior Técnico. É um homem que tem dedicado a sua vida aos materiais compósitos. Lidera um grupo no Instituto Superior Técnico, onde estuda estes materiais e o seu comportamento material e estrutural, enfim, associado a várias situações, nomeadamente também à parte sísmica. Nesse momento vai mostrar um bocado esse trabalho que tem realizado nessa área. Para além disso, coordena um futuro aerocódigo para estes materiais, portanto é uma pessoa que neste domínio está perfeitamente à vontade para nos dar uma aula sobre o assunto. Portanto, eu passava a palavra ao professor João Ramôa Correia e peço a todas as pessoas para seguirem esta apresentação.
Obrigado, professor Aníbal Costa. Eu não sei se veem o meu ecrã, era a primeira pergunta.
Sim, está
Aparece o ecrã completo.
Sim, está bom.
Perfeito. Portanto, eu preparei a apresentação em inglês porque foi-me dito que havia participantes que não eram portugueses, portanto eu irei falar então em inglês. So once again, many thanks, Professor Aníbal Costa, for the kind introduction. Thanks also to Professor Sousa Oliveira for the very kind invitation. Well, this presentation has two main goals. First, to provide an overview of composite materials used in civil engineering structures, and also to present some recent studies about their potential use in seismic areas. I would like to acknowledge my co-authors, Drs. Firmo, Bonilha and Garrido, and our PhD students, Sousa, Martins and Proença. This is the outline. I will start with the summary of FRP composites for civil engineering. And next, I will address the seismic behavior of 4 different FRP products. Strengthening with CFRP systems, GFRP reinforced concrete columns, GFRP frame structures, and sandwich panels for the rehabilitation of building floors. And I will finish with some concluding remarks. So starting with the overview of FRP composites, these materials are basically constituted by 2 phases: the fiber reinforcement, which has high strength and linear elastic behavior, and this would raise a red flag for earthquake engineering, and also the polymeric matrix, which includes resin and usually also filler and additives. Well, the matrix has much lower strength than the fibers, but on the other hand, it has 3 very important functions: load transfer and stress distribution between the fibers, their protection from environmental agents, and also keeping them in position, namely when they are loaded in compression. Here I listed the 4 types of fibers most often used in FRPs: glass, carbon, basalt, and aramid. They are available as rovings with continuous fibers, or mats, which can have short or continuous fibers with different orientations and patterns. In this table, you can see that all fibers have very high strength, and the most relevant difference between them is the modulus, which is maximum with carbon and minimum with steel. Now let's look at the thermoset resins that are more often used with FRPs. You can see that their mechanical properties are relatively similar, being 1 to 2 orders of magnitude lower than those of the fibers. The most relevant difference between these resins is basically their ability to bond the fibers and their durability, which is maximum in epoxy and minimum with polyester. So the philosophy in the development of FRP materials is that depending on the specific requirements of a given application, it is possible to select the most appropriate manufacturing method and to combine different types of fibers, varying their type, content, position, and orientation, the type of polymer resin, and also the additives and fillers to obtain specific properties. So there is plenty of room for engineering or multifunctionality. Let me give you two simple examples. One is this hybrid profile, where glass fibers are used in most of the profile, but where carbon fibers, which are more expensive, are used in the flanges where they are more useful. And also the sandwich panels used in this building with several functions, not only structural, but also thermal insulation and lighting. Well, in this slide, I divided the structural application of FRP materials in four main groups. The external strengthening of concrete structures, where strips and sheets are often used. The internal reinforcement of concrete structures with FRP rebars. Hybrid structures, where profiles and sandwich panels are used in combination with traditional materials. And all composite structures, where these components are used alone. And here, this is a bit crowded slide. I listed for each of these four types of FRP products, the main research subjects that have been relevant, I would say worldwide. I marked in bold the ones that we have been studying at IST, and in blue, the topic of this conference, the seismic behavior, which you can see is relevant for all types of products. So this will be the focus of the remainder of this presentation. So for each FRP product, I will try to show some highlights, first of all, about their main features, and then some highlights of research activities at IST. So we will first see CFRP systems. Here we did not do much research. Then GFRP bars for concrete columns, next GFRP frames, and finally sandwich panels. So starting with CFRP systems, they are, which are probably well known for most of you, they are available in two main types. Strips with unidirectional carbon fiber rovings. They are already procured and are simply bonded to the substrate of the member that we want to strengthen with epoxy adhesive. And then sheets with uni or multidirectional mats, which are molded and cured in situ, so applied by hand layup, being impregnated and bonded with epoxy resin. Here you can see some typical ranges of variation of mechanical properties of these CFRP materials. You can see that the modulus is roughly similar to steel, structural steel, while the tensile strength is about 10 times higher in components that are, of course, extremely lightweight. Here I show some common applications of CFRP sheets in wrapping columns and also beam-to-column joints where they provide confinement. And here I try to summarize the principle of this confinement effect. So when concrete is compressed in the axial direction, due to Poisson effect, it tends to expand in the transverse direction. And here the FRP wrap will prevent such lateral dilation, promoting a triaxial stress state. And so the practical consequence is that both the compressive strength and the ultimate strain of confined concrete will increase very significantly compared to normal concrete. So when we go to the structural scale, for instance, vertical member under lateral loads, this will result in a significant increase of axial load, but also of lateral displacement, ductility, and energy dissipation. Here you can see another application, in this case of CFRP strips, installed in a cross shape for the shear and seismic strengthening of concrete walls. So the strips, in this case, are bonded with epoxy to the substrate, and they also have these mechanical anchorages to prevent premature debonding, which is a typical failure mode in these systems. And finally, you can see here another application, in this case of FRP sheets in masonry walls, bonded vertically or in a cross shape, so for flexural and shear strengthening. And below, a more recent alternative to the so-called conventional FRP systems, which are the textile reinforced mortar systems, which are more compatible with the masonry substrate. So the second topic is the seismic behavior of GFRP reinforced concrete columns. It's a topic that we started to address recently at IST in the context of the thesis of Sousa. So first, let me describe the main features of GFRP bars. In terms of constitution, they are typically made of vinyl ester resin and rovings, so only axial fibers, it's where we need them. They are available in similar diameters to steel bars and provided with different surface finishing, which already provide quite reasonable adherence to concrete. In terms of geometry, they are available as straight bars, that you can see here, and bent bars with different shapes, hooked, U-shaped, and closed stirrups. Here you can see ranges of variation of different engineering properties. I highlighted those for glass FRP because they are the most often used. So the tensile strength generally is around 1000 MPa, so twice that of steel. The problem is the elastic modulus, which is around 50 MPa, so 4 times lower. Here you can see some typical applications in aggressive environments, so either coastal areas or bridges where de-icing salts are used in the winter. So basically the motivation of this thesis is that in spite of their potential, there are doubts and I would say legitimate concerns about the use of this type of reinforcement in vertical members, especially in seismic areas. So basically the objectives were to assess the influence of GFRP bars in concrete columns, to evaluate the lateral deformation and energy dissipation capacity of concrete columns, and also to study the confinement of the concrete core provided by these closed GFRP stirrups. So to this end, so far we did 3 full-scale tests in columns, 1 with steel rebars as a reference, and 2 with GFRP bars under monotonic and cyclic loading, and also the numerical simulation of these tests. Here you can see the geometry of the specimens. As I mentioned, they had full scale, square section with 300 millimeters, 1.8 meters of height. So the steel and GFRP longitudinal rebars were designed to provide similar flexural strength. And here you can see a detail of the closed GFRP stirrups used in the columns. Here you can see some details of the specimen's preparation. So you can see that the footings, they had only steel rebars. And here you can see the columns after demolding. And here a detail of the strengthening with the CFRP sheet at the top of the column to avoid crushing due to load application. This is a view of the test setup. So in the first stage, we applied an actual load corresponding to 20% of the actual load capacity of the columns, and then a lateral load either monotonically or cyclically using a reaction wall. So in terms of failure modes, as expected, all columns failed due to flexure, with extensive cracking next to the bottom of the columns and formation of a plastic hinge in the steel RC column and what we call an inelastic hinge in GFRP reinforced concrete columns. In these cases, failure occurred actually in the GFRP bars, as you can see here in these photos, due to compression and possibly with some influence of shear. Well, in terms of lateral load displacement curves, here you can see the results obtained for the monotonic tests for GFRP and steel column, and cyclic test that we did only for GFRP. So we can see 3 different stages of the behavior: an elastic stage until cracking, then an inelastic stage with cracking progression until spalling of the concrete cover occurred in both columns, and then an inelastic stage where the concrete core remained confined by the stirrups. So basically, when we compare the GFRP column to the steel reinforced column, we can see that it was possible to obtain a similar lateral load capacity, but however, the lateral deformation capacity and the ductility were reduced by 25 to 30%. So this obviously needs to be taken into account, and we need to do further studies to analyze this reduction performance. On the other hand, the GFRP stirrups were able to provide relatively effective confinement of the concrete core, enabling this lateral deformation capacity. So for the numerical study, we used the software Athena, so to develop 3D finite element models of the columns. Material properties were obtained from tests, as well as the bond slip law used for the GFRP bars. And at this stage, for concrete nonlinear behavior, we considered the default parameters from the FE code. So we need still to do some additional research in this topic. So here you can see the results obtained in these preliminary simulations. So the comparison between experimental and numerical results for the three different tests. So for the monotonic response, I would say the response, the predictions are relatively accurate. So we were able to capture well the lateral load capacity, but of course the models were not able to simulate the spalling of the concrete cover, which then triggered the buckling of steel bars and the failure of the GFRP bars in compression. So as future steps, we plan to do, hopefully in the next few weeks, tests in 13 additional columns with GFRP bars with different actual load levels, and also with hybrid reinforcement. So here the idea is to combine GFRP with stainless steel bars that typically are used in very aggressive environments to explore the recentering potential of GFRP with the energy dissipation of stainless steel. And we expect with this research to contribute to the drafting of design recommendations for this application. Well, for the third topic, it has to do with the seismic behavior of all FRP structures, so GFRP frame structures, and it has been developed in the context of an FCT project. So first, let me explain what are FRP profiles. Here in the left picture, you can see the so-called first generation profiles. Well, they basically copied the shapes of metallic construction, so standard thin-walled sections. And later, the composites industry developed the so-called second generation profiles, which are these multicellular sections for bridge decks. In terms of constitution, each wall of one of these profiles is made of different layers of fiber reinforcement that combine rovings, mats, surface veils, all embedded in a polymeric matrix, typically of polyester. Here I listed ranges of variation of different properties because material properties differ among manufacturers. First of all, let me recall the behavior is linear elastic for most failure modes. So the longitudinal strength is similar to several steel grades, but the behavior is orthotropic. So lower strength in the transverse direction, low shear strength, and also low values of elastic moduli when we have glass fibers. In terms of connection technology, that is relatively underdeveloped. These profiles can be joined by bolting, again, copying the practice of metallic construction, which has been proved to be quite inefficient, bonding, a combination of these methods, or mechanical interlock. Here you can see some applications in new construction of bridges and buildings, and also in their rehabilitation, where the non-corrodibility and the lightness of these materials have been key properties for their selection. So this project on the seismic behavior of FRP frame structures, well, the motivation was, I would say, twofold. So first of all, the proneness to premature and local brittle failure at the connection. So we realized that the technology available was not effective. And then, of course, the same doubts and concerns about the seismic response of GFRP frame structures, for which I should say there is no design guidance available right now. So in this context, the objectives were, first of all, to develop material adapted connections and frame structures with adequate ductility and energy dissipation capacity, where we try to explore the combination with metallic materials, and then at the structural scale to study the seismic response of such frame structures. So in terms of methodology, the study focused on 3 levels: beam to column connection tests, 2D frame sway tests, and finally 3D frame shaking table tests. So at the connection level, the study focused on 2 different sections of GFRP profiles: square tubular and I section. And for each shape, we developed 2 different systems. So for the tubular shape, we developed first the sleeve system with a stainless steel part that is positioned inside the GFRP beam and column. So these parts are not visible. And a cuff connection system comprising an external stainless steel part, which is much easier to install. For the I section profile, we studied the same cuff system and an additional one involving stainless steel cleats as an alternative to FRP cleats. So this is the test setup, a conventional setup to test these connections under monotonic and cyclic loading, where we assess these different performance parameters. And let me show you just a brief overview of some results. So for the tubular profiles with the sleeve connection systems, where we varied the position of the position and also the number of the bolts, you can see here a summary of load displacement curves of the different series. And you can see that for this specific series, where we increased the edge distance, it was possible to avoid shear out failure in the GFRP, which is very brittle, promoting instead bearing failure in the GFRP, which is more ductile, and also the yielding of the steel part. And this led to this nonlinear response. Here you can see another series, the same tubular profile, but now with the cuff connection system, where we varied the thickness of the steel plate and also its length. And as expected, increasing the amount of steel increased the stiffness and the strength of the connections, but still with a quite nonlinear response. And here for the I section profile with cleated connections, where we varied the thickness of the cleats, so from 3 to 8 millimeters, and also the number of bolts. So as expected, the thickness of these steel cleats had a significant influence not only in the stiffness and strength, but also in the ductility. So for thinner cleats, the stiffness was quite low, and the response was highly nonlinear because they started to yield for quite low levels of load. While for thicker cleats, although the response was stiffer, we also obtained premature failure modes in the GFRP material. So finally, the option was to adopt intermediate thickness cleats because the response were more balanced. Here, just as an example, you can see a summary of cyclic test results for 2 of these series with cleats with 3 and 6 millimeters of thickness. So in all series, you can see that quite marked pinching effects were observed. And comparing both, you can see that with 6 millimeters of thickness, we were able to obtain higher stiffness and strength, and also wider hysteretic curves, so associated with higher dissipated energy. So we also did some FEA of these connection tests. This is just an example of the simulation of these I section profiles with cleated connections. We used Abacus. So stainless steel was modeled as nonlinear, and for now, GFRP was modeled as linear elastic. You can see that the response was quite accurately predicted, but failure in the GFRP material is still pending on the development of fracture models that are ongoing in our group. So the second step was the study of the behavior of the 2D frames. So we used dissections with the cleated connections as they were the best performing ones. And we studied 3 different frames: a single frame, then a frame with a bracing system with stainless steel braces, and then one with a lightweight partition walls to investigate their effect. So here in this left plot, you can see the results of the monotonic tests. So you can see that the single frame presented very high flexibility and deformation capacity. So only for very high deformations, there was damage in the materials and the connections. And of course, this was reflected in the cyclic tests, where very limited energy dissipation was observed. And then with bracing systems and with the walls, the stiffness and strength increased, and so did the energy dissipation capacity. In the third and final stage of this study, which is still ongoing in our labs, we are doing shaking table tests in 3D frames, where we are using the connections that were developed earlier, and we are looking at frames with and without the bracing systems, and we will also investigate the influence of the loads at the floor levels. So far we already did the modal analysis, including the influence of the bracing systems, and in the next few weeks we will start doing the dynamic tests with imposed earthquakes. So we get to the fourth and final part of this presentation about FRP sandwich panels. And here I should say that this topic is not directly concerned with their seismic performance, but a closely related topic, which is their potential use in building floors rehabilitation. So let me first show what are these sandwich panels. Very briefly, they are constituted by two FRP face sheets, which are thin, stiff, and resistant. And these sheets are bonded to core material. There are different alternatives, which is typically thick, light, more flexible and less resistant, and generally is thermally insulating. Here you can see the structural application of these panels in a big roof of a building, where the lightness, the freeformability, and the insulating properties of these panels were quite relevant. Here you can see another application, the roof of a railway station, where also the lighting possibilities of these panels were explored. And here, a vehicular bridge, where not only the lightness, but also the speed of execution were key factors for selecting this system. So here in the top of this slide, I summarize these main advantages that are offered by sandwich construction. And some of these advantages, they seem particularly interesting for rehabilitation, namely of old buildings with masonry walls. In fact, these sandwich panels, they represent a very limited weight increase compared to heavier traditional solutions, which may possibly prevent the need to, or at least limit the needs for strengthening the existing structure. And there is also potential to improve, depending on the connections between these panels and the walls, to improve the out-of-plane behavior of masonry walls. Well, in spite of this potential, of course, there are many challenges that need to be faced for this application. Here I listed several that we addressed at IST, and in the next 3 minutes, I will just show some brief highlights on these 4 topics. So shape and material optimization, creep behavior, connection technology, and fire behavior, which is of course a major concern. So for the first topic, we did material characterization tests on various potential materials to be used, not only in the face sheets, but also in the cores of these sandwich panels. And we investigated the optimization, not only of the materials, but also of the shapes of these sandwich panels for different applications. We also studied the creep behavior of these materials because they are viscoelastic. So not only the sandwich panels, but also these different components, the cores and the face sheets, where we looked at the influence of temperature and also of the load levels. Another important topic, the connection technology. We addressed it at 2 levels. First, the connections between the sandwich panels and masonry walls using steel angle profiles. And then, of course, the technology to join panels laterally. So we developed bonded connections, and also snap fit or mechanical connections. And finally, of course, the key topic of fire and elevated temperature. So we have been studying the behavior at elevated temperature of the components. So here you can see as an example, shear tests in different core materials as a function of temperature, and here the reduction in the properties as a function of temperature. And then the fire resistance behavior of sandwich panels without any protection and with board protections, either adherent or with an air cavity. Here you can see a panel after being tested for fire. And here you can see in this plot the mid-span deflection increase as a function of exposure to fire time. Without any protection, the resistance was lower than 30 minutes. And with these two protections, it was possible to exceed the 60 minutes of fire resistance. So to conclude, I should say that among the different FRP products that are available, CFRP systems are already a well-established technique for seismic retrofitting. It offers several advantages over conventional techniques. For GFRP concrete columns, their use in seismic areas is in fact very challenging. Compared to steel columns, they were able to present similar lateral load capacity with an effective confinement of the concrete core. However, one needs to take into account that lateral deformation capacity and ductility are lower than with steel conventional reinforcement. For FRP frames, we found out that stainless steel parts appropriately combined with FRP enable relatively ductile connections. However, when we move to the structural scale without additional bracing systems, the energy dissipation is quite low. And finally, for FRP sandwich panels, there seems to be potential for building floor rehabilitation, especially because they offer several functions in a single layer. But this application, of course, entails several challenges that need to be studied in further depth. And with this, I conclude my presentation, and thank you very much.
Muito obrigado pela excelente apresentação que foi feita, no fundo, com os vários domínios de aplicação dos materiais compósitos. Eu agora punha, enfim, temos cerca de 60 participantes, punha à consideração dos participantes quem é que deseja fazer alguma pergunta sobre esta apresentação do professor João Ramôa Correia. A apresentação também foi um bocadinho mais longa do que estava previsto, portanto também não temos muito tempo, mas eu gostava só de, já agora de pôr uma questão simples. Eu vi ali no dimensionamento destas principalmente das fibras, normalmente utiliza-se muito uma, não sei se vocês utilizam, que normalmente como as áreas são distintas, nós utilizamos muito para dimensionar no fundo o número de camadas e a espessura, uma fórmula do Priestley. Vocês utilizam isto ou não?
Sim, o professor está-se a referir para efeitos do confinamento.
Exato.
Exatamente, sim.
Dimensionar de pilares, não é? Quando fazemos o confinamento de pilares, no fundo, para definir o número de camadas e, no fundo, a sua espessura, o Priestley tem uma forma que nós já o testamos algumas vezes e aquilo funciona muito bem, dá resultados ótimos. Ou seja,
eu diria que
práticos, é muito bom.
Esse foi um dos primeiros trabalhos e, de facto, a precisão é muito boa. Depois disso, como é normal na investigação, tem havido uma série de colegas que se têm dedicado a refinar e a introduzir pequenas melhorias na fórmula. Eu diria que a fórmula original, para a engenharia, é suficientemente boa. Mas tem havido propostas novas, sobretudo de um grupo de Hong Kong que tem trabalhado muito nisto, o professor Teng, e tem havido pequenos refinamentos dessa fórmula original.
Uhum.
Mas sim, quer dizer, eu acho que essa fórmula continua a funcionar para efeitos de projeto e de aplicações práticas, quer dizer, muitíssimo bem, tem lá os princípios todos, não é?
Sim, senhor. Estava a ver se tinha alguma pergunta aqui, se alguém queria pôr alguma questão aqui no bate-papo, mas pronto, eu acho que agradeço a sua intervenção, a sua excelente intervenção.
Muito obrigado.
Passava a palavra à Mónica para passarmos ao ponto seguinte, a tal tertúlia ou no fundo discussão sobre o futuro